Hello, myself Maheshwari. I am from BSc MPC first year from Government City College, Naipur. My topic is valence shell electron pair repulsion theory. In 1914, Sedgwick and Powell proposed Westport theory on the basis of repulsive interaction of the electron pairs in the valence shell of the atoms. This theory further developed by Nehlum and Gillespie in 1950. Main postulates of Westport theory. The shape of a molecule depends upon the number of valence shell electron pairs, bonded or non-bonded, around the central atom. Here we know what is bond pair and what is lone pair. Bond pair, electron pair which is shared between two atoms and is responsible for covalent bond formation is called bond pair. Wherein lone pair, electron pair which is not shared between two atoms is called lone pair. Here I am taking one example, that is NH3 molecule. Nitrogen electronic configuration is 1s2, 2s2, 2p3. The outermost valence shell electronic configuration is 2s2, 2p3. Hydrogen 1s orbitals are overlapping with nitrogen p orbitals to form NH3 molecule. In NH3 molecule, 3 are bond pair and 1 is lone pair. Here we can see that. Next, electron pair in valence shell repel one another since their electron clouds are negatively charged. These electron pairs tend to occupy such positions in space that minimize repulsion and so maximize distance between them. The valence shell is taken as a sphere with electron localizing on the spherical surface at maximum distance from one another. A triple bond is treated as if it is a single electron pair and the 2 or 3 electron pairs of a multiple bonds are treated as a single super pair. When 2 or 3 resonating structures can represent a molecule, the Westport model is applicable to any such structure. Repulsion strengths. Lone pair is greater than lone pair is greater than bond pair. And triple bond is greater than double bond is greater than single bond. Steps to determine the geometry. First, we determine the central atom. Second, draw the electron dot structure and Bohr diagram. Third, find the arrangement of electron pairs. Fourth, find the arrangement of bonding pairs. Fifth, determine the geometry based on bonding pairs. Models are linear, trigonal planar, tetrahedral, bent, trigonal, pyramidal. These are for molecules with only paired electrons around the central atom. Linear, 2 atoms attached to center atom. 0 unshared pairs means lone pairs are 0. Bond angle is 180. Type AB2, example BeF2. Trigonal planar, 3 atoms attached to center atom. 0 lone pairs. Bond angle is 120. Type AB3, example AlF3. Tetrahedral, 4 atoms attached to center atom. 0 lone pairs. Bond angle is 109 degree 5 minutes. Type AB4, example CH4. Trigonal bipyramidal, 5 atoms attached to center atom. 0 lone pairs. Bond angle is equatorial less than 120 and axial less than 90. You have a doubt what is axial and equatorial. Here we can see a diagram. In the diagram, AX is axial and EQ is equatorial. Its type is AB5. Example is PF5. Octahedral, 6 atoms attached to center atom. 0 lone pairs. Bond angle is 90. Type AB6. Example SF6. These are for molecules with both paired and unpaired electrons around the central atom. Bent, 2 atoms are attached to center atom. 2 lone pairs. Bond angle is 104 degree 5 minutes. Type is AB2E2. Example H2O. Trigonal pyramidal, 3 atoms attached to center atom. 1 lone pair. Bond angle is 107 degrees. Type AB3E1. Example NH3. The common molecular geometries are all derived from these 5 electron domain geometries. They are linear, bent, trigonal planar, bent, trigonal pyramidal, tetrahedral, T-shaped, seesaw, trigonal bipyramidal, linear, T-shaped, square planar, square pyramidal, octahedral. Here we can see a table. This table is most important to find the molecular geometries. In this table, ED electron domain and LP lone pair and BP bond pair and type and electron domain geometry and molecular geometry and examples are there. When we get electron domain 2 and lone pair 0 and bond pair 2, then its type is AB2 and electron domain geometry is linear and molecular geometry is linear, and example for that is BeCl2. And when electron domain 3 and lone pair 0 and bond pair 3, then its type is AB3. Then electron domain geometry is trigonal planar and molecular geometry is trigonal planar. Example is BF3. In this process we can find molecular geometries. So we can learn this table. The difference between valence bond theory and Vesper theory. Vesper theory is the theory that predicts the geometry of a molecule. Valence bond theory is a theory that explains the chemical bond in a covalent compound. It based on the repulsions between lone electron pairs and bond electron pairs. It based on the overlapping of a orbitals in order to form a chemical bond. It does not give details about orbitals present in atom of a molecule. It gives details about the orbitals present in atoms of a molecule. It indicates the geometry of a molecules. It does not indicate the geometry of molecules. It does not indicate the type of bonds present between atoms. It indicates the types of bonds present between atoms. Limitations of Vesper theory. It fails to predict the shapes of several isoelectronic species. Two electronic species can differ in geometry despite the fact that they have same number of valence electrons. It fails to predict the shapes of transition metal complexes. The model does not take relative size of substituents into account. The atomic orbitals overlap cannot be explained by Vesper theory. The theory makes no predictions about the lengths of the bonds, which is another aspect of the shape of a molecule.